All right, so we're looking at sum and difference identities. I've got a typo here. It should just say sum and difference identities, period, not just for the cosine. We're looking at the sum and difference identities for sine, cosine, and tangent. These are identities that I will give you a cheat sheet for on a quiz or a test. Okay? However, you still need to recognize them in order to know when to use them. You want to have them for the most part. You want to know them for the most part. And really what those cheat sheets are for to make sure that you've got your pluses and your minuses in the right spots, things like that. But you want to have the general idea of what they look like. The reason why is because in order to apply them in our goal number 2, to evaluate trig expressions, solve trig equations, or prove trig identities, you need to recognize where they are and how they show up. Okay? So here are the identities. I'll give you a moment to copy them down, and then I will point a couple of things out. Something to keep in mind when you're using these is how to read them in their condensed form. So you'll notice that I gave you the formula for both the cosine of an angle plus an angle and an angle minus an angle, all in the same formula. Those signs read like across the top or across the bottom, not both ways. So in other words, the cosine of A plus B, that's your top sign right there. That means that you're going to use the minus for the formula. If you had A minus B follow across the bottom, that means you're going to use the plus sign here. So notice that for the cosine, whichever sign you have, it switches in the formula. But notice for the sine, does it switch? No. So that's something to keep in mind. On the tangent, you've got both the sign that you're given, and then it does switch on the bottom. So just make sure that you guys understand how to read that. All right, so let's take a look at why this can be useful. All right, so I'm asking you guys here to find the exact value of each without using a calculator. Okay, now notice that 15 degrees is not one of the angles that we learned on the unit circle, right? That's not one that we have memorized. What I can do, though, is I can split that 15 degrees into either an addition or a subtraction of two angles that I do know around the unit circle. Okay, so Ian, what would be an example of two angles that could add or subtract to 15 that I know on the unit circle? Very good. So what I could do is take the sine of, and rewriting that 15 degrees as 45 minus 30 degrees. All right, the most common mistake people make here is then to distribute the sine in and say that that's the sine of 45 minus the sine of 30. Do we ever make life that easy? No, we don't. So this is going to use one of those formulas. You just need to be able to look at your piece of, you need to be able to see this and recognize that that's what you need to use, first of all. And then you need to use it correctly. So make sure that you find the sine formula, and then make sure you're finding the one, or following the sign with the minus and putting in the correct sign in your formula. Who can read off to me what I should have here? What should I write next? Look at your formula. Yep. Sine of 45, cosine of 30. Yep, so the sine value has the sign that doesn't switch. And then all that you do is, so you take the sine of one angle, cosine of the other, and then you switch where if I took the sine of 45 on the first go around, I'm now going to take the sine of 30 times the cosine of 45. And then I now have angles that I can evaluate. So what is the sine of 45 degrees? Root 2 over 2 times, what is my cosine of 30 degrees? Root 3 over 2. Very good. Minus, what's the sine of 30? 1/2, very good. And the cosine of 45? Root 2 over 2. Okay, so notice that when you simplify this, that very first expression multiplies out to be root 6 over 4, right? And the second one is going to be root 2 over 4, so I'm going to write them as 1 fraction over 4 since they have a common denominator. And then that would be my final answer for that. All right, the tangent of 7 pi over 12 is a similar idea. You're trying to find two things that add up to 7 pi over 12 that are angles that you know. The trick to this one, you guys, is that think about around the unit circle. What are the, when we're in terms of radians with pi, what are the denominators that we know around the unit circle? So you know pi over 6. Yep, so Shane just did them in order. We know denominator of 2, so like pi over 2s. We know pi over 3s, pi over 4s, and pi over 6s, right? I don't know pi over 12. But what I can do is split that top number 7 into two things that add or subtract to 7 that are at least even number, well, not even, but two numbers that would divide 12 into a lower denominator, if that makes sense. So what are two numbers that add to 7 that would divide 12? 3 and 4. Yep, it's as easy as that. So we've got that this is going to equal the tangent of 3 pi over 12 plus 4 pi over 12. And then what's nice about that is that 3 pi over 12 simplifies down to pi over 4, which is now something that I know. And 4 pi over 12 simplifies down to pi over 3, which again is something that I know. Now we need to use that tangent of a sum of two angles formula. So look at your cheat sheet, or your formulas. The tangent should end up being a fraction. What do you have on the top of the fraction? Tangent of pi over 4. You keep the sign on the top, so plus the tangent of pi over 3. And then divide it by 1. Change the sign on the bottom, so minus, and then the multiplication of those two things. The tangent of pi over 4 times the tangent of pi over 3. All right, so go through and evaluate what you know. What is the tangent of pi over 4? 1, very good. What is the tangent of pi over 3? Root 3. It would be root 3 over 1. So you can see why I had you do the memorization of the unit circle is because now you're into more complicated things. You really don't want to be diddly-daddling around on this stuff, right? You want to be able to come up with it fairly quickly. We've got 1 minus, and then notice it's the exact same pieces. So the tangent of pi over 4 we already said was 1 times, and we said the tangent of pi over 3 was the square root of 3. Okay, something that you need to know is that I've told you guys you don't have to rationalize on something, and don't write this down, just kind of watch. Like I told you, if you had 2 over the square root of 15, I told you you could just leave it, right? And the reason why is because when you have 2 square root of 15 over 15, does that really look that much better? Does it simplify it all that much? Not really. However, when you have a situation where you've got a root on the bottom and something added or subtracted onto it, rationalizing this actually is going to make it look better, so I will expect you to do it, and so will the textbook. So what do you do here to rationalize this thing? Multiply by the conjugate of the top or the bottom? Of the bottom. So the conjugate down here is 1 plus the square root of 3. That's going to be 1 plus the square root of 3 on top. I'm going to kind of bring this up here so I have some space. So on the top, when you multiply that all out, you get 1 times 1 is 1. The multiplication of the outer and the inner is going to give you plus root 3, which will be 2 root 3. and then root 3 times root 3 is 3. The bottom, you've got a difference of perfect squares, so it's just the first value squared, 1 squared is 1, minus the second value squared, root 3 squared is 3. And then if I simplify this, I have 2 root 3 plus 4 by adding my 1 and my 3. And on the bottom, this condenses to negative 2, and then what do you see? It splits it. So it gets negative root 3 minus 2, and you can see that that is a significantly better looking answer. That's why we will rationalize those. Any questions on that? Okay. We need to write the expression as a single trigonometric function. This one is as easy as it looks. So this one, all you have to do is recognize that that looks like which formula? Which formula does that look like? Guys, I'm low on time. Please follow me. It looks like the cosine. Does it look like the cosine of an angle plus an angle or the cosine of an angle minus an angle? Plus. Remember that, look at your cosine formula. The signs are switched on the cosine formula. So this is actually going to be equal to the cosine of an angle that they've given you plus the other angle. Make sure you see why that's a plus. Then we would simplify that down into the cosine of 10y. Okay, moving on. I've got 2 examples that I do want to get through, you guys, so please bear with me. All right. It says to prove the identity. One thing I want to point out is that in the past I was telling you guys to work on the side that's more complicated. Okay? In the case where you have a side where you've got a multiple of an angle, it is actually easier to work on this side even if it doesn't look more complicated. So if you ever have that situation where one of your angles is more than just x, you want to work on this first. It's easier to expand it than to condense it. Okay, so how do we handle this? This one you're going to have to kind of go through a series of steps. So to break this up, what you want to do is write it as the addition of 2 angles. I can write this as the cosine of 2x plus x, and then use that expansion formula. I'm going to kind of zip through this, so let me know if you need me to pause. The cosine of an angle plus an angle, if you look at your formula sheet, turns out to be the cosine of the angle 1 times the cosine of the angle 2. So here, you have 2x and x. And then minus, because the cosine switches signs. And then you have the sine of the first angle times the sine of the second angle. We still have 2 angles that we need to simplify down. How do you think I'm going to break those up? Same way. So I'm going to write that as the cosine of, I'm going to write that as the cosine of x plus x. That's still times the cosine of x. Minus, and then I'm going to write this as the sine of x plus x times the sine of x. And then I'm going to break each of those ones up. So it does expand out, but it actually condenses pretty quickly. This first one is going to end up being the cosine of x times the cosine of x minus the sine of x times the sine of x. That's just by the expansion rule. All of that is still times the cosine of x minus, this breaks up into the sine of x times the cosine of x plus, you keep the sign on this one, and then sine of x times the cosine of x. And again, you can just kind of look at the expansion rules if you don't see where I'm getting that right offhand. I'm just literally looking at the sine of a plus b. How does it expand? Okay, when I look at this very first one, I notice that this is just going to be written as the cosine squared of x by condensing minus the sine squared of x by condensing times the cosine of x minus, this next term is actually 2 times the sine of x cosine of x, because it's the same exact term added on. That still is times the sine of x. And we're almost there. So now what we're going to do is distribute the cosine through to get the cosine cubed of x minus sine squared of x cosine of x. And on this term, we're going to multiply the sine of x in, so I get 2 sine squared of x cosine of x. And then you'll notice that we've got two terms that are the same things, just different coefficients, so I can combine them into the cosine cubed of x minus 3 sine squared of x cosine of x. And now we've got pieces that match the first and the last. So that one is just a matter of taking the time to expand it all out. Let me really quickly, and if you guys can just stay after the bell for 2 minutes, I'll get through it really quickly. You'll want to see it for the homework, so bear with me. It's the last one. This one, it says to solve the equation exactly. Notice that you've got angles both as double angles and as single angles. So what do you think you have to do? You need to break down those double angles by expanding them into x plus x and then breaking them down. So I'm going to look at this very first term and split it into the sine of x plus x times the cosine of x equals, this is going to expand out by the cosine of x plus x times the sine of x. I'm going to kind of condense a couple of steps because it's very similar to what we just did on that last problem. When you expand the sine of x plus x, it is going to be the sine of x times the cosine of x plus the sine of x times the cosine of x. The same two terms together, right? So I guess I can take a second and write it. But you get the sine of x times the cosine of x plus the sine of x times the cosine of x, which are going to condense. That's all times the cosine of x. Equals, this is going to expand out to be the cosine of x times the cosine of x plus the sine of x, actually not plus, what should it be? It should be, yep, a minus, so let me change that real quick. Minus the sine of x times the sine of x, and all of that times the sine of x. All right? These two terms are the same, so this is 2 cosine, sine, cosine, but then I'm going to end up multiplying this in. So this, stay with me just for a couple minutes, guys, I know, I'm sorry. This is going to be 2 sine of x, and then I'm multiplying that in to become cosine squared of x. That came from just adding the two terms and distributing the sine, cosine in. On the other side, you'll notice that you're going to get cosine squared minus sine squared, and then I'm just going to distribute this sine of x in as I go. So the first term is going to have a sine of x, and then a cosine squared of x. The second term is sine squared times a sine, which will be sine cubed of x. All right, notice that these pieces are the same, so when I subtract this one over, I'm left with just 1 sine of x, cosine squared of x equals, and actually I'm going to add the sine cubed of x over in the same step. That equals 0, and now we get some really nice things. Between the two terms, what can you pull out? Yep, so you pull out a sine of x, you're left with cosine squared of x plus the sine squared of x, and what happens there? Yeah, that whole thing drops down to 1, so we lose it. So all we have to answer is, where does the sine of x equal 0? So think on your unit circle, sine of x is your y value. When is the y value 0 on the unit circle? Y value being 0. 0 and pi. Y value is on the x-axis. So it's at every multiple of pi. So you would write pi times k, and you're done. Thank you for bearing with me. Here's your homework. And yes,
it's going to be on Schoology.
Yes, it is due tomorrow. It's on Schoology except for that note at the bottom, you guys. I didn't teach to number 46. It's a problem that doesn't look like what I've taught, but but example 6 in the book is exactly like it. So you want to follow example 6 for number 46. The rest of this should all be pretty straightforward. That will be due on Wednesday. Remember to study for your quiz as well. This is going to be good review for the quiz also. It has all the same kind of stuff going on in it.